Okay, let's go ahead. Part number 8, which is like the task, it includes a lot of different things we've done in stats. So here we go. Let's first make our scatter plot, and we're going to do it on a piece of graph paper. Let's switch over to that. There we go. So I first want to look at my data. Okay. I'm going to know that this is x. Our age, usually time is always on the x-axis, and this is going to be my y. Okay. So my ages go from about let's see, 1 to 10, so I can do that in 10 squares going across. And here, my data starts about 70 and goes to 135, so basically between 70 and 140. However, you can see how they're going down by like 15, 10-ish, so I want to not just start my labeling at 70, let's say, but be safe and go down to like 50. That way I make sure if my line goes down, it's not going to get cut off. So I'm going to start around 50 here and use a break from 0 to 50. So that's things you have to plan out before you start. You don't want to just start graphing and hopefully everything fits. So here we go. This is my age right here. This is going to be my height. There we go. So we can label this 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Oh, 10. Good. Bigger. Alright, and then I'm going to do a small break. I'm going to start at 50. That'll give me a little bit of buffer. And we'll have 60, 70, 80, 90, 100, 110, 120, 130, and 140, and that should cover my highest point, which was 135. Let's just go ahead and put the data on here now. We have 1 comma 73, 1 comma 73. Remember, these are approximations. 2 comma 85, 5 comma 107, 6 comma 113, 7 comma 120, 8 comma 124, 9 comma 130, and 10 comma 135. So pretty close, highly correlated data set. Okay. B says go ahead and find the line of best fit. Now let's go with about right there. I'll do mine in pencil just in case I need to redraw it. Okay, so I'll use that for my line of best fit. It looks like I'll have my y-intercept will be 70, and then I can use this point and this point for my slope. So as you're drawing this line, you want to be thinking about, well, what 2 points will I use for my slope, and what will my y-intercept be? So at least we'll know we have that y-intercept is 70, and I'm going to use, looks like 2 comma 85 and my 8 comma 124 for calculating my slope. Alright, so let's switch it back over. There we go. we have find the best fit. Okay. Now it does ask us for the equation first, but first I need to calculate my slope. So as I mentioned before, I'm using 2,85 and 8,124 for my slope. All right, so that's going to be slope equals 124 minus 85 over 8 minus 2. And bottom's going to be 6. And top's going to be 39. And 39 over 6 is 6.5. So slope of 6.5. And we did the B earlier, just off the graph, and we said that was 70. So with these two, I now know my equation, which is, once again, always start y equals mx plus b, and it's going to be y equals 6.5 x plus 70. Okay. What does our slope mean in the context of this problem? Okay, so it's always good to look at the units. So you could say, okay, if you want to do the fraction, that 39 over 5, the units for the y were centimeters, or height, centimeters in height, and the units for the x were years for their age. So whenever they say context, make sure you think about units and labels. That'll help you figure it out. So basically they're saying for every 5 years of age, you grow as a sample of children, heights are about 39 centimeters taller for every 5 years of age. Another way of looking at it is the 6.5, and that has the same units, just think of it as 6.5 over 1. So that would be 6.5 centimeters per year, or for every 1 year. That's another way of looking at it. So we're going to go with that one. The average height of the children will grow 6.5 centimeters every year. How about that? Okay, and write that out. The average height of children will increase 6.5 centimeters every or per year. So the key to answering this question is knowing what are the labels and the units. And you can talk about and use the fraction, or you can use the decimal. Depending on the problem, either one might be good, or maybe one's better than the other. I think the 6.5 is better in this certain problem. But it's just whatever really makes sense. That's what you go with. Okay. And the y-intercept in this problem, well, according to our sample, the y-intercept, remember, it's b equals 0, which is the same as, and b equals 70, which is the same as 0, 70. So they're saying, well, someone with a height of 0 or unborn, more or less, is, with age of 0 is going to be a height of 70, which doesn't really, not really true, but, for our data, that's what we got. Okay, so, and it's also the start of our graph, but for the age of 0, it'll be 70 centimeters tall, which we know is not true, but remember, that's how scatter plots are. They're just an estimation. Okay. All right, use our best fit using your line, a best fit, estimate the height of a 12-year-old. Okay, so if we actually go back to our best fit line, okay, there it is, and we kept extending this out, age to 12. By the way, I should write age down here and put years in parentheses. Okay. So if we extend this up and extended our line of best fit out, right about there, okay. And it looks like it would go right about here, which is about, that's 160, so we go with about 160. Another great use for the line of best fit is to predict. All right. So from the graph, it said to use the line of best fit, and we're going to estimate, so we got a height of 160 centimeters. And we could also use our graph, our equation that we got up here, 6.5x plus 70. That should give us something similar. So if we did that, y equals 6.5 times 12 years old plus 70. Okay. That should equal something close to 160. So 6.5 times 12. Do that. 6.5 times 12. Get 78. And 78 plus 70 is 148. So you can tell our equation and our graph are not quite on the same level, but statistically they are still pretty close. They're, you know, not perfect, but only 12 centimeters away. That's a pretty good estimation. Okay. So what kind of relationship do these data have? If we went back to the graph, you could probably describe this as a strong positive correlation. That's the most direct way to describe this. There's a strong positive correlation because the data is so close together in a positive way. As one goes up, as the age gets higher, so does the height. That's positive. All right, and that concludes the review for the Statistics Assessment Part 2. Okay, good luck.